Good day, everyone. So this is me again, Sir Nivero, and welcome to our class today. Um, today we'll be discussing about special products. So by the way, these special products were chosen by mga few. I think there are only four special products that I mentioned in. I will be mentioning in this um, video. So in this video, we will find special products. So basically, we need to derive these products in using, if you're going to follow the module, no? So basically, you can do manipulatives there, and of course, factors of certain polynomials. So that's it. All right. So to start with, we have now let us try to consider a square. No? So let's say yellow square, and then let's try to cut this yellow square into um, some parts of no into four other measurements. No? So take note that the area of a square is, if you still remember the area of a square. So the area of the square is basically what? A is equal to S square, right? A is equal to A is equal to S square. So there. Or the area of a square is equal to the side times side or the side square, right? S square. So now let us try to cut this square into smaller pieces of shapes. No? So let's have this one, orange square. And then this one, the blue one, blue rectangles, and then the last one is a smaller square, right? Now let us put some measurements here. For example, in this orange one, let's say that is 7, and then this one is 1, right? So basically, whatever the measurement here, since it's a square, so it will just follow that the side here will be 7. Same with this one. This is a rectangle. Since I note them as the same measurement, no, since they have, take note that all the objects that have the same color are practically equal, no, in measurements. No? All right, so the blue rectangles are equal. So meaning the one side is 1, and then the small square is the purple one is basically you think is the area. So we'll try to see what is the area of this orange square. So again, you just have to follow this one. Now for the rectangle, you can just follow the area of rectangle. If you still remember, this is the area of the rectangle. All right. So it's length times width, right? So now let us try to find the areas of these figures here. So this one, 7 times 7, that's basically 49. By the way, the unit here is centimeters, so I didn't include it. Anyways, it will just make sense later. So for this one here, how do you get the area? So you have this is the length, right? I mean, this is the width. Now, what do you think is the length here? Length is, all right, so it's 7 since they have this, they are using the same side with this one, the orange one, all right? So meaning this is 7. And how about this one, the smaller, the other blue rectangle? So basically that's 1. What do you think is the width here? It's also 7, right? So basically, if you find the area, 1 times 7 is 7, and then this one is also 7. And then what about the smaller square? So that is, how do you get the area of that? So first is you need to find what is the measurement of the sides of the square or the side of the square. So basically, it's just 1. Take note of this and that. It's just 1, meaning the area will be, using S square, it will be 1 square unit or square centimeter. All right. Now, what's with this? What's with this? Now, in order for us to get the area of the bigger square, right? Um, uh, how do we get again? How do we get the area of the bigger square, the yellow one earlier? How do we get the area of that? Thinking that we have the 7 and 1, and also 7 and 1 here. How do we get the area of that? Okay, let's try to continue. So the orange one plus the two blue rectangles, plus the small square is just equal to the bigger square, the yellow one. So how do we get the area of this? If we try to add the area of these shapes, this is 49. This is, since this is 2, so 7 plus 7 or 2 times 7 is basically 14. And this one is 1. So if you try to add those together, it will eventually equal to what? All right, it's 64. All right. But how did you get 64 without, if we won't um, be, if you're not going to include these figures in the structure here um, given here, we're just going to put the measurement 7 1 7 1. How do we get the area? All right, so we just add those sides and then we square it, right? So 7 and 1, 7 plus 1 is 8. All right, so 8 squared is how much? It's 64. Now with that, we can now derive the formula for what? Some square of binomials. Now let us try to use some variables in order for us to represent any numbers. Let us try to use x and y. So for this side, 7 earlier will be replaced by x and 1 will be replaced by y. So if that's the case, the area here is x squared, right? Then this one here is xy. This one here is xy also. And this one is y squared. Take note that if you're going to follow the pattern earlier, you're going to add this together, right? To get the yellow one, this is x squared plus xy plus xy. That's basically 2xy, right? So, and we have the area of this, which is y squared, which is equal to what? X plus y squared. Because here, in this case, we use the x and the y variables, no? So we just have to add them and then also on this side and then you square it. That's the formula for a square of binomial. All right, so again, what do you call that? A square of binomial. Now let us try to expound the following given. Okay, so let us try to expound these two expressions here. Now, before we proceed, these are the formulas. So why is it not minus is included? Why? Because it can be also done in minus. So I didn't include it in the illustration, but if you're going to follow lang um, the same process earlier, it will eventually come to what? This pattern, no? X squared minus 2xy plus y squared. So this one, x minus quantity x minus y squared can be written as x minus y times x minus y. And take note that the result of squaring a binomial, these two here, are what we call the perfect square trinomial. So how do you say, how do you determine that a trinomial is a perfect square? So you have, the first term is a square and the last term is a square. The middle term is twice the product of the square root of the first term and the last term. So again, twice the product of the square root of the first term and the last term here. Now, let us try to use these patterns in these following examples. So you must try. So if you want to try the examples, you can pause the video and continue, try to solve using the formula. All right. Now, using the pattern, no? So x squared, and then this square the first term, we have x squared, and then twice the product of the two terms. So 3 times x, that's 3x, and times 2, so and we square the last term, it will just equal to what? All right, so that blocked by my face. All right, so that is just equal to x squared plus 6x plus 9. Now let us try having a negative middle sign. So quantity 2x minus 4, what is a square? So again, just follow the pattern here. Square the first term. So 2x square, quantity 2x square. And then since it's minus, so the middle term will be minus. Then do not copy the sign of the terms. No? Since you are using a pattern, just follow what is this. Do not include the sign of this negative 4. So since it's already minus here. So twice the product of the first and the second term. So 2 times 2x times 4, and then plus the square of the last term. So 2 times 2x is 4, times 4. If you're trying to, if you're going to simplify this, this will be 4x squared. Again, 2 squared is 4, x times x is x squared, minus 2 times 2 times 4 is 16. So negative 16x plus 16. Again, 4x squared minus 16x plus 16. Okay? So we're done with square of a binomial. Let us try to derive another form of special products. So again, consider a square, yellow square. We have this, again, orange square, and then we also have this two rectangle, um, rectangle figures, no? Um, excuse me. And then a square here, meaning we cut the whole, the bigger square, and then this will be, uh, here it is a smaller rectangle again, and then there's another smaller rectangle, and then the small square. So again, these similar color figures are equal, okay? So meaning we can combine them. So first, let us put some values on these the measurements um, of these figures. So for this square, the orange one, of course, if we get the area of this, again, we're going to use the area of the square and the rectangle here. So basically, this is 49, and then this one, how do you get the length here? So the length will be what? It will be 7, right? So 7, so 3 times 7, that's 21. So same with the other blue. And then the green one, this is just 1 times 7. So by the way, the purple one is 3 times 3. So that's 9. And then the green one is 7. And 7 here, this is 3. 3. The area is 3. And then the red one is 1. Again, one square centimeter. So if that's the case, how do we get the area of the bigger square? So we need to combine them together. So if we try to break it down, it's like this. So the bigger square, smaller square, smallest square, pair of two bigger rectangles, and then another set of rectangles, and then the last set of rectangles. Now, sir, is it necessary for us to put the position here? For example, this one, the two squares. Um, Later it will make sense, no? But eventually, I mean, it doesn't necessarily have to be like that, no? So it's a matter of perspectives, no? So if you want to put it like that, then okay. If you want it in another form, then so be it. All right. Now, if we are going to find the area of this yellow square, what do we have? What are we going to do? So we need to add the areas of these figures. So how did we get 121? So we'll try to add this area. 49 plus 9 plus 1. This 2 here is times 2. So 42, since 21 and 21 is 42. And then this one is 14. So 7 and 7. And then this one here is 6. 3 plus 3 is 6. So with that, if you're going to add this together, you may try to verify this 121. But If that's the case, how do we get 121 uh, using the pattern that we had earlier? This one. How do we get the 121? If we are to, without these figures here, without the divisions of this figure, how do we get the area of the bigger square? So we add these sides, so 7 plus 3 is 10, plus 1, 11, and then also here. So 11, since it's a square, 11 square is 121, all right? Now, let us try to use some representations, so similar earlier. So we replace the numbers with variables. So we 7 as x, y as 3, and z is 1. So same with up here. So x times x is x squared, and y times y is y squared. Z times z is z squared. And then this two here, x times y. This is also x times y. This is xz, the green ones, and then this one is yz, or sorry, xyz, yz. So this is the arrangement is yz. Sorry. So earlier you might be asking, sir, why is it that you always have to arrange it like that? So in algebra there is one rule that states that the arrangement of terms, no, it must go with the degree and also alphabetically. Sorry. So if this is the area here is x square, sorry, so this is x square, right? And then this is y square, and this is z square. Since this is twice, so two of them, x times y times plus x times y, so 2xy plus twice of this, so 2xz, and then twice of this also, which is yz, so 2yz. So again, I arrange it in this form, no, because I want to follow the pattern wherein alphabetically um, and with the degree of the terms. No? So basically, um, uh, we have to follow some rules in this one. Right? But anyways, if you were going to substitute some values there, it will just eventually come up with the same answer. It's just the arrangement that matters. No? If you try to express it in simplest form. But in substituting, the values are just the same. So that's the case. X plus y plus z square is in this format. There are actually three of this. Okay, another three of this form. So we have from x all positive, we have the negative z, so x plus y z square, and then this is the formula. And we also have the negative y, no, x minus y plus z square, which is given in this formula. And we also have the negative y and the negative z, so which is x minus y minus z square. So again, I did not include the figures of the representation of these polynomials, but if we are going to put it into figures, it will just have a um, take a long period of time. So in this case, uh, I'm just showing you the usually the first ones. So let us try to use these patterns, no, for examples. So we call this square of a trinomial. Now let us try to expound the following. So again, if you want to practice, you can pause the video and try to do the pattern. So with these patterns, no, you just have to follow the patterns. So if these are all positives, you can use this pattern. So first things first is you have to identify what is your x, what is your y, and what is your z. So this is my x, my y, and z. So with this x, y, z here, you replace all those values with their corresponding values. So again, I colored the x as red and y as blue, green for z. So let's now um, upon during the substitution, no, so you have to carefully take note of the parentheses. Why? Because if you're just going, for example, in this case, if you're just going to write it in this form, that's different at all. No? That's different. So since your y is 2a, you have to enclose it in a parenthesis to emphasize that 2 is included in the power or the raise, okay? The exponent 2. And then let us try to simplify this. This is just equal to e squared. And then this one, 2 squared is 4, so 4a squared. And then this is q squared. Then 2 times 2 is 4 times ae, so alphabetical. And then 2 cubed. And then this one is 4a cubed. All right. All right. So for this one here, again, just follow the pattern. So since it's the negative z, so we're going to follow this one. So again, you identify your x, y, z. Your x here is 9a squared plus 4b squared. I mean, your y is 4b squared, and then your z is negative. Do not include the negative symbol. No? 3c squared, your z only is 3c squared. Why do we skip the negative symbol? Why? Because why the negative there, the pattern already established the symbols here. So if you're going to include the negative in the value of z, this sign here will change. All right, we established it using the pattern here, so do not include the negative sign. All right, so if that's the case, you replace all these values with their corresponding um, values, no? I mean, you replace these variables or representation with their corresponding values. So 9a quantity 9a square 1 plus quantity 4b square quantity square plus quantity 3c square plus 2 times 9a square times 4b square minus 2 times 9a square times 3c square and so on. So let us now simplify this. Okay, so you square all this. Since this is enclosed in the parentheses, you also have to square the number. So 981, 8, 2 times 2 is 4, and this goes on. So this is 2 times 2 is 18 times 4. How much is that? 18 times 4, or 9 times 4 is 36 times 2, 72. And then 9 times 3 is 27 times 2 is 4, 54, sorry. 2 times 4 times 3 is 24. So again, do not include the negative sign since you already established the symbols here. Right. So that's all for the square of trinomials. You may refer to the module for more examples and practice exercise. Now, let us try to move to another kind of special product. No? First is we have to consider a square ABCD, and then we cut that square in this part here or any part, right? And then we create another square, no, which is in this part here. Let's name this GECF, or right, or GFCE. Now, that square there, what's the significance of that? Now, you see these remaining blue ones. How the question there is, how do we get the area of that? All right. So first is we have to establish some values, so or measurements. For example, in this one, let's say the measurement here is x, and the measurement of the size of the smaller square is y. Now, question is, how do you get the area of the remaining blue ones, or this one? Yeah, first, how do you get the area of that one? So taken into consideration, this is the remaining one. So again, why is it y? The variable y is written there. Take note that the smaller square earlier has the side of y. So if you cut this part here, it will also equal to y. So if that's the case, the measurement of the side in this part up until here is y. Now, if we are going to arrange that figure, right? We this rectangle here, if we try to to rotate that, okay, if we try to rotate that, so, and then since it has the same length with, it will now have the same length with this smaller rectangle, we can place this smaller rectangle beside it, right? Again, how did you get this figure? So it came from this bigger rectangle, the one we cut, and then this smaller rectangle is the one that is beside it. No, the small it's the remaining part where we cut the line, right? Where we cut the square, the bigger square. After getting rid of this smaller square. Now, take note of this measurement here. What's the measurement here? It's x. And how about this one? This is y. So how'd you get x? This is the measurement here. We just flipped it around. And then this one is y. We just followed this figure here. Now question, how do we get the area of this hole? Okay. So take note this one here. How do you get the measurement on this side? On this side. So if you're going to get the measurement of that, diba, this is x. The whole thing is x. The whole thing is x here. So this one or this one here, the whole thing here is x. And then what will happen to the measurement of that? What will remain here if you're going to take the part in this part here? So what do you think is a measurement? It's so x minus y, right? Because you subtracted. So now we get the concept of these two patterns here. So it's x plus y. So we add this to get the area of this. And then we also have to multiply it with, since it's length times width, right? So the area of the rectangle, since it, if you merge this together, if you merge these two figures, it will just eventually become a bigger rectangle. So the measurement or the area of that bigger rectangle is just equal to quantity x plus y times quantity x minus y, which is, right? Sorry, my PowerPoint got destroyed. So which is x plus y, quantity x plus y times quantity x minus y is equal to the square, all right? So again, where did you get this bigger square? So earlier, the blue one, remember? But the area of this, since we have it as x, so the square of this is x squared. And then we also have this as y. So the area of this is y squared. Now, if you're going to get the remaining ones of this one, diba, we just have to subtract the bigger square by the smaller square. So that's it. We call it sum and difference of two terms. Again, sum and difference of two terms. Now, so again, my formula, my presentation is not really doing well. So anyways, so x plus y, quantity x minus y, so x is equal to x squared minus y squared. So let us try to simplify these patterns, these binomials. So this we are going to use the pattern that we arrived earlier. So enough of this. You can actually verify these patterns using the concept, no, the traditional concept of FOIL method. First, outer, inner, last. So in this video, we're not going to use that, but we're going to focus on the formula. So let's continue. So W minus 5 quantity times W plus 5. So since, how are you going to establish, how are you going to say that these factors here are sum and difference? So again, it should be, I mean, their first terms must be the same, should be the same, and the last terms are should be, can be expressed in the same manner. Okay, so sometimes it may not look like the same, but there are times that you have to square root or square, no? So you have to really investigate the given. Now, how are you going to identify that the given product or this part here is a difference of two squares? So again, the first term is this one here is a perfect square and is subtracted by another perfect square. Okay, so again, the first one is a perfect square and should be subtracted by another perfect square. So we get w as x. So I put it in red and then 5 as blue. So we now simplify w squared minus 25. And also this one, 2x minus 9 times 2x plus 5. So 2x squared minus 9 squared. That is just 4x squared minus 81. All right, now let us try to use this. Let us now continue with a last pattern that is in my that is in the module. So let us try to observe this figure. All right. So it's a cube, but it's not a 2 by 2 cube that has the same what's this measurements for each cube, smaller cubes, right? So the volume we get of a cube is the length times the width times the height. So if the height is a plus b and the width is a plus b and the length is a plus b, so of course the volume is a plus b cube. So if that's the case, we now use this pattern. So if you see the red one, that is the bigger cube. So that's eventually a cube. And then the rest of these black and red ones are just small. Okay. So these are all a square b. And then also this the one that is faced with the blue ones, smaller blue ones, are just ab square. Okay. And then we also have this one. Take note of this. This is the blue part here measures b, so meaning the cube of this is b cubed. Okay, so how did you get three of this? Remember that there are 8 objects, 8 figures that are formed in this cube. So meaning we have this in the some parts of the cube, and we also have this in some parts of the cube, and this one, which is the blue one. This one is a bigger one, so this is a cube. All right. Now, if you're going to add this together, this is just to get the cube of the whole cube. Since the whole cube has the different dimensions, no? So to get the measurement, I mean the smaller cubes has different dimensions. No? So to get the area of the bigger cube, the sum of I mean, to get the volume of the bigger cube is you have to get the area of the smaller cube. Sorry, to get the volume of the bigger cube, you need to get the volume of the smaller cubes, and then you add them together. So it will just come up to a cube plus 3a squared, b plus 3ab squared plus b cubed. So these are the patterns. So quantity a plus b cubed is equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. And then we also have a minus b cubed is equal to a cubed minus 3a squared b plus 3ab squared minus b cubed. All right.